Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today lecture is about chemical bonding. In the last class, we discussed about the various types of bonding, which include the ionic bond, covalent bond, coordinate covalent bond, hydrogen bonding, and metallic bonds. In the last lecture, I discussed about the ionic bond and covalent bond, and in today's lecture, we will discuss the coordinate covalent bond, hydrogen bonding, and metallic bond. So let's start the coordinate covalent bond. Coordinate covalent bond is a type of alternate covalent bond. Covalent bond is that bond which is formed by the sharing of electron by each atom. But this covalent bond, which is known as coordinate covalent bond, is a little bit different. That in this case, the share pair of electron is donated by one of the atom. For example, we can see the example of coordinate covalent bond in the bond of ammonia and boron trifluoride. In this case, in the ammonia molecule, nitrogen contain a lone pair of electron, which can be donated to the boron, which is an electron deficient species, and form a coordinate covalent bond. So it is formed by the sharing of electron, therefore it is known as covalent bond. But as both the electron is donated by one of the atoms, so this type of covalent bond in which the both the electron is donated by a single atom or a single molecule is known as coordinate covalent bond. The coordinate covalent bond, one species is known as the and the other is known as the acceptor or receptor. In this case, in example of ammonia and boron trifluoride molecule, the ammonia is known as donor molecule while the boron trifluoride is known as acceptor or receptor. So this type of bond in which both of the shared pair of electron is donated by one of the molecule is known as coordinate covalent bond. Another example of coordinate covalent bond we can see in the molecule of ammonium ion. Ammonia molecule, the nitrogen contain the lone pair of electron, while hydrogen ion have no electron, and both the electron of nitrogen is donated to the hydrogen to form a covalent bond. Therefore, it is known as coordinate covalent bond. So, in boron trifluoride and ammonia complex molecule, the bond between the ammonia and boron trifluoride is a coordinate covalent bond, and similarly in ammonium ion the bond between the nitrogen and hydrogen, which is denoted by an arrow, is a coordinate covalent bond because both the shared pair of electron is shared by the ammonia molecule. Similarly, another example of coordinate covalent bond is the hydronium ion. When water molecule combine with the hydrogen atom, the lone pair of electron of oxygen donated to the hydrogen ion and form a coordinate covalent bond. So generally the coordinate covalent bond is formed by the donation of lone pair of electron by an electronegative atom such as nitrogen or oxygen, and as both the electron is donated by one of the atom, therefore so characteristics of coordinate covalent bond that in this type of bonding, one of the atom or molecule which donate the lone pair of electron is known as the donor, while the other atom which accept this shared pair of electron is known as the acceptor or receptor. The bond is represented with an arrow pointing toward acceptor from the donor atom. As we can see in the molecule of boron trifluoride in ammonia, ammonia is the donor, so the arrow is from ammonia to the boron trifluoride. After sharing of electron pair, each atom gets stability and complete its octet, so it's become stabilized. These coordinate covalent bond have lower melting and boiling point than ionic compound because this is a relatively weak bond as compared to ionic bond. Sharing of electron take place in a different direction, so it is a directional bond. and the direction is from donor toward the acceptor. It is a weaker bond than ionic bond. The second type of bond is the metallic bond. Metallic bond result from the electrostatic attraction between metal cations and delocalized electron. Metallic bond is a term used to describe the collective sharing of C of valence electron between several positively charged metal ions. For example, one can see over here the metallic bond in sodium. So we can see that there are positively charged species, and as the sodium have one valence electron, so each positive ion have one electron, but the electron is not specific to that positively charged nucleus, but it's a type of C of valence electron. So the electronic configuration of sodium is 1s2, 2s2, 2p6 and 3s1. So the valence electron is which you can see in the image is actually the 3s electron. So it contains one electron in its valence shell, and that valence shell is 3s shell. So in the solid state, metallic sodium feature an array of sodium ions that are surrounded by a sea of 3s electron. However, it would be incorrect to think of metallic sodium as an ion because the sea of electron is shared by all the sodium cation, quenching the positive charge. Factor affecting the metallic bond, the total numbers of delocalized electron. As the numbers of delocalized electron increases, the metallic bond will be stronger. The second factor is the magnitude of positive charge held by the metal cation. As the magnitude of positive charge increases, the bond becomes more stronger. The ionic radius of the cation, if the ionic radius is smaller, then the bond will be stronger. So it's inversely related. But the delocalized numbers of delocalized electron and magnitude of positive charge is directly proportional to the metallic bond strength. So if the numbers of electron increase and number of positive charge increase, then this bond will be stronger. And if the ionic radius is smaller, then the bond will be smaller. We can see over here three types of metallic bond, the sodium metallic bond, magnesium, and aluminum. In this case, aluminum is more stronger metallic bond as compared to magnesium, and magnesium have more stronger bond as compared to sodium because the sodium have one positive charge and one delocalized electron, while magnesium have two delocalized electron and aluminum have three delocalized electron. As the numbers of delocalized electron increases, it become more stronger. And as the positive charge is held by the metal cation increases, also the bond strength increases. So we can see that aluminum have more positive charge, therefore it is more stronger bond as compared to sodium and magnesium. And the ionic radius from left to right decreases, so the aluminum bond, metal bond is more stronger. So the metallic bond strength is affected by three factors: the numbers of delocalized electron, the magnitude of positive charge, and the ionic radius. The ionic radius is inversely proportional to the strength of metallic bond, while the magnitude of positive charge and the numbers of delocalized electron is directly proportional to the strength of metallic bond. The nature of metallic bond account for many of other physical properties of metal, such as conductivity and malleability. Characteristic of metallic bond: as a result of powerful metallic bonding, the attractive forces between the metal atom is quite strong. In order to overcome these forces of attraction, a great deal of energy is required. Therefore, due to this reason, the metallic bond have high melting and boiling point. The metallic bonds can retain its strength even when the metal is in its melt state. For example, gallium melts at 29 degrees centigrade but boil at 2400 degrees centigrade. Therefore, molten gallium is non-volatile liquid. Some other characteristic of metallic bonds are mentioned over here, that when light is incident on a metallic surface, the energy of photon is absorbed by the sea of electron that constitute the metallic bond and excited to a higher energy level. And these excited electrons quickly return to the ground state emitting specific light. and when it emits specific light, it gives a shiny metallic luster to the metal. So all the metals are generally shiny because it absorbs photon and the electron excited to a higher energy state, and when it come back, it emit light. So therefore, it's generally all the metals are generally shiny in nature. Metallic bonds are non-directional because the electrons are not shared with just one atom or in a single direction, but is shared with many other neighboring atoms in all directions, and the electrons are in the form of C. Therefore, the metallic bonds are generally non-directional in nature. The last type of bonding is hydrogen bonding. Hydrogen bond is the force of attraction between a hydrogen atom which is covalently bonded to an electronegative atom, and that electronegative atom must be nitrogen, oxygen, or fluorine, and the hydrogen bond donor and another electronegative atom bearing non-ferrous electron, the hydrogen bond acceptor. For example, one can see over here the example of water and ammonia. In water and ammonia, the nitrogen non-ferrous electron attract the hydrogen, which is covalently bonded with oxygen, which is an electronegative atom. So in this case, the water molecule is considered as a hydrogen bond donor because hydrogen is attracted by the nitrogen atom, and the ammonia molecule is known as the hydrogen bond acceptor. In the second image, you can see that the ammonia molecule is a hydrogen bond donor while the water molecule is a hydrogen bond acceptor. Since an interacting system is generally denoted by donor hydrogen, and then the hydrogen bond is represented by dash dash with acceptor, where the solid line denote a fully covalent bond and the dotted and dashed line indicate the hydrogen bond. Hydrogen bondings are two types. One hydrogen bond is known as intermolecular, occurring between separate molecules. For example, one can see over here that there are two carboxylic acid molecules, and the two carboxylic acid molecule, the one of the hydrogen is attracted by the carbonyl oxygen atom, and this type of molecule, as the hydrogen bonding exists between two molecules, therefore it is known as intermolecular hydrogen bonding. The second type is intramolecular hydrogen bonding, which occur among the same molecule, the hydrogen donor and the hydrogen acceptor is present in the same molecule. For example, one can see over here hydroxybenzoic acid, and in this case, we can see that the hydrogen donor, the OH group, and the hydrogen bond acceptor, the carboxylic acid group, both present in the same molecule. Therefore, this type of bonding is known as the hydrogen bonding. So, in today's lecture, we discuss the coordinate covalent bond, the metallic bond, the factor which affect the metallic bond strength, and then discuss the hydrogen bonding and types of hydrogen bonding. Thank you.